Hello everybody, welcome to our video solution to problem 2 from quiz 7. And we're still working on sequences, but here we're going to actually verify sequence convergence using the definition of sequence convergence rather than just using some properties of sequences and some already given sequence convergence results. So in this problem, we're given the sequence of powers of 6/10, right? 0.6 to the n. And so our d, right, this looks like 0.6, comma 0.6 squared, comma 0.6 cubed, etc. And it should seem reasonable because zero point 0.6 is less than 1, that when you multiply it by itself, you should get something smaller. And every time I multiply by 0.6 again, I should be getting smaller, something smaller and smaller and smaller. And so reasonably, I should be converging to 0, right? And this is what we want to prove, actually, is that this thing converges to 0. And the directions are explicit about that. We want to actually use the definition of sequence convergence. So the definition that we gave, this non-standard definition, since we want it to converge to 0, we need to prove that every 0 coin contains a tail of the sequence D. So remember, a 0 coin means, okay, so I need to choose some radius for the coin, and by convention, maybe we'll take this Greek letter epsilon. So this is going to be the radius of the coin. So I come over here and I do 0 minus epsilon. I come over here, I do 0 plus epsilon. All right, so we know that this distance is epsilon, this distance is epsilon, right? That's what we call it, the radius. And of course, we could imagine there being this nice coin. Right? Notice how the coin is circular, just like these parentheses on the end, which tell you we don't include the endpoints. And this is the 0 coin. The 0 coin with radius epsilon. So this is just an arbitrary one, right? Epsilon could be any positive number. So we just need to choose some random one, and we need to show that it contains a tail of this sequence D, meaning we can go out far enough, right, and then start the sequence, right? So remember a tail, which maybe we write something like this. This would mean start it at 0.6 to the positive n, right? And then you keep going, 0.6 to the n plus 1 and 0.6 to the n plus 2, right? This would be a tail of D. And we don't know what this n is. That's the whole problem, right? We need to find some n such that the corresponding tail, every element in that tail, right, every term in the sequence is going to end up on this number line inside this 0 coin. Okay. Well, let's see. That means we want some n such that if, say, some little n is at least big N, right? So if you take anything right past big N, then 0.6 to the little n is contained in the 0 coin. That means it's between 0 minus epsilon and 0 plus epsilon. Of course, I can simplify this, right? This is negative epsilon and this is positive epsilon. So I would need negative epsilon to be less than 0.6 to the n and 0.6 to the n to be less than epsilon. Okay, now I know that 0.6 is positive, and when I raise it to a power, right, it's always going to stay positive. So I don't even really worry about the left-hand side of 0, right? Everything hopefully is going to show up on the right-hand side and inside this coin, so long as I make this big N large enough. Okay, so really I don't need to worry about a minus epsilon here. I can actually just replace minus epsilon with 0, right? Just because we know this is always positive. Okay, well, because it's always positive, and of course it's never going to equal 0, this first condition on the left is not a condition we need to worry about. It's this condition on the right that we need to worry about. How do we make sure that 0.6 to the n is less than epsilon? Okay, so 0.6 to the n less than epsilon. How do we make sure this happens? Well, This n in the exponent is annoying, and I would like it down, and I'd like to solve for it by itself. So what I'm going to do is take the natural logarithm. So I'm going to say, let's take the natural log of 0.6 to the n. And because the natural log is an increasing function, it's not going to change the order of this inequality, right? Right? Natural log increasing function looks like that. So if you increase the input, you increase the output. Okay, now why do I take the natural log? Well, it's because I have this log property that says I can take exponents and pull them to the front. So I have n log of 0.6 is less than, oops, I'm writing log, because professional mathematicians tend to write log instead of ln. Okay, now again, I'm trying to solve for the natural, rather for n, and so I want to divide by ln of 0.6. And when I do this, something strange is going to happen. All right, so I divide by ln of 0.6 on both sides, but I don't get to just write n is less than. And the reason why is because, well, let's look at this natural log function a little more closely. Where does it actually cross the x-axis? Well, let's see. If the output is 0, then I'm asking, what do I, this has something to do with the exponential function, right? So if ln, let's write it up here, if ln of something is equal to 0, then that means that e to the 0 is equal to that something. Oh, but e to the 0 is equal to 1. Ah, so this is the natural log of 1. So that's where it crosses. Well, 0.6 is less than 1, which means, okay, 0.6, right? Maybe that's somewhere over here. That means the natural log is negative. And so when I do this divide, I'm dividing by a negative number, and that reverses the inequality. But this is actually a really good thing, because I'm trying to figure out how big I need to go out, right? How far I need to go out so that this condition holds. And if n was less than, that would seem weird, right? That wouldn't be giving me a tail. That would be giving me a head, right? But now this says, okay, you just need to go out past this point. So there we go. We need n to be greater than ln of epsilon over ln of 0.6. So what do? We can set big N equal to, well, this is not actually going to be an integer, probably. I mean, it could be, for example, if epsilon is equal to 0.6, but usually it's not going to be. So what do we need to do? Well, this is going to be some number, and when I get that number, I need to make n an integer which is greater than it. So this is going to be, we could say, well, we could make it the smallest, right? That would be the nicest. So the smallest integer greater than ln of epsilon over ln of 0.6. Now I'm going to put parentheses around smallest, though, because it's not really necessary, all right? I don't really care that I get the most efficient tail, right? The first tail that works. I just need a tail that works. So I could have just said n is the integer, or is an integer, right? So in which case this would be an, alternatively, an integer greater than ln of epsilon over ln of 0.6. Because if n is such an integer, and little n is at least as big as n, then we just run these backward, right? This is all if and only if here. And we'll get that 0.6 to the n is less than epsilon. That is, our points are going to be inside this 0 coin. Okay, well, that's how we can use the definition to prove sequence convergence. All right, obviously this is more challenging than what we did in problem 1. In problem 1, you just get to use these nice, properties, and we just assume that 1 over n to the k converged to 0, for example. And that's the way you want to do it in general. Why do we need to worry about the sequence definition? Well, there's the sequence convergence definition. It's the same reason why you need to worry about limits of functions in Calculus 1. In the short run, you don't have a ton of problems where you use it. You usually just end up using differentiation rules, right, in that class. But in the long run, if you want to actually prove things in a more theoretical setting, or if you have functions where the normal differentiation rules don't immediately apply, for example, when you might have some piecewise functions, you actually have to use the limit definition, right? That'd be the only way you can solve these problems. So we practice on these more simple problems to get you ready for the more complicated piecewise ones. All right, take care, everybody. We will see you next time.